today is the day that you are going to find out what this table is all about. You have seen this table for 3 years, in maybe 4 in your information sheet, and besides giving you a few helpful hints about what some of the polyatomic ions formulas are, it hasn't really been something we've used. So let's find out what it's about. These are all called half reactions. The table is called the standard electrode potentials. Now, you know what potential is. Potential is something to do with potential difference or volts. So here are a bunch of, it's called E volts. It's a standard potential of a certain cell. Still making no sense, I'm sure. Let me carry on. They set out in order, minus 3,05 up to plus 2,87, and this is called increasing oxidizing ability. Excuse me, and increasing reducing ability. Now, when you are looking at these tables, you must always look for the one that you like. And the DBE's papers, if you happen to use them, don't look like this. They are the whole thing upside down. Well, that's not particularly helpful because we're going to learn everything about how we do it if it is, in my opinion, the right way around. So we're going to look for the one we like. And how do we know which one we like? We like it because it starts with lithium and potassium, which is, and an electron. So it is like over there. Let's just expand that a little bit and you'll see what I mean. So it's L-I-K-E. Okay. So that's your first thing, is you need to make sure you've got the right table. And then we are going to see which are the best reducing agents and which are the best oxidizing agents. And then we're going to relate them to one another. So today we're going to look at a couple of what are called half cells, and you'll see how they relate to one another, and you'll become more and more familiar on how to use this table. It's actually really, really pretty handy and not terribly difficult. So let's look at that. Now let's look at how we get this loss and gain of electrons, who's who in the zoo. So what we're going to do is we're going to do the following. We're going to take a look at where do we find copper and where do we find zinc on this table. And over here I find the zinc. And over here I find the copper to copper 2 plus. Over there. And now if we take a look at that, we can say that the zinc is higher up, and therefore it has a greater reducing ability, which means it is more likely to get oxidized. The oxidation is at the top and the reduction is at the bottom. And what we'll end up doing is we'll end up saying, I'm going to write the zinc backwards and the copper forwards, because this is a table of reductions, and therefore forwards is reduction and backwards is oxidation. So I'm going to just do that a little bit slower. Over here I am told going up is increasing reducing ability. If you're a good reducing agent, what happened to you? You were oxidized. So the things that undergo oxidation are at the top, the things that undergo reduction are at the bottom. So I'm going to write that one backwards and that one forwards. And we always look for this C shape when we are looking for spontaneous electrochemical reactions. Then what happens is I'm going to do the following. I'm going to write those half cells out. I go zinc backwards, Zn becomes, now you'll notice it's a double arrow. It could be reduction or oxidation. I've now decided that it is oxidation, so I use a single arrow, Zn to Zn2 plus 2 electrons. The copper is going to be reduced, so it goes Cu2 plus 2 electrons becomes Cu. What do I see happening? These electrons cancel. What's the overall reaction? Cu2 plus zinc gives me Zn2 plus copper, and that is a electrochemical cell that has been set up. You can put the aqueuses in and the solids in and the aqueous and the solid if you want to. So how do we draw that out? Firstly, we need to remember that we have got oxidation always occurs at the anode, because these electrodes have got specific names, and reduction always occurs at the cathode. How do I remember that? I remember that O and A are both vowels, oxidation anode, and reduction cathode, R and C are both consonants. A little English here in the physical science. So the zinc loses electrons and becomes Zn2 plus. The copper gains electrons and the copper 2 plus gains electrons and becomes copper metal. So how do I write that as a symbol, a shorthand? As we know, scientists love shorthand. It's laziness, at least efficiency, is just an overdeveloped form of laziness, and physical scientists are very efficient. We're not going to call them lazy, we're going to say efficient. So let's go. We're going to go zinc solid slash in a Zn2 plus aqueous 1 mole per cubic decimeter solution is linked by a salt bridge double slash into copper 2 plus, which is aqueous solution of 1 mole per cubic decimeter in a with copper solid dipped into it. What does this look like? The more reactive metal forms the anode. That was the one that was up at the top, oxidation anode, and leaves the less reactive metal to form the cathode, reduction cathode. Electrons flow from the more reactive to the less reactive metal, in other words, from the anode to the cathode. Let's look at this picture in a little bit more detail. This is called the Daniell cell, and the Daniell cell is our classic zinc copper cell, and we have got zinc metal dipped into a zinc solution. It could be zinc nitrate, it could be zinc sulfate, it could be a number of zinc solutions, but it's zinc Zn2 plus ions. What happens? The zinc Zn2 plus ions, the zinc loses electrons and becomes Zn2 plus ions. Where do those electrons go? Through the wire. Where do they land up? At the copper. On this side, what's happening? Copper 2 plus ions are gaining electrons and becoming copper metal. And that's what's happening over here. And we've got those two half reactions written over there. That's the net cell reaction. This thing here called a salt bridge connects them. Normally what you put into the salt bridge is something called potassium nitrate, and what happens? All the time I'm getting more and more of these Zn2 plus ions. So this solution would be very, very positive. How do I make it negative? I drop some nitrate ions in there. Boom. On this side, I've got this copper, and I'm losing negatives all the time. I'm losing the positives all the time, and therefore this solution is becoming very negative. So when it becomes negative, what do I do to make it fix up? I put some K pluses in there to keep it nice and balanced. So what does the salt bridge do? It maintains electrical neutrality, and it does that by supplementing ions on either side. Here's a pretty picture of what one really looks like. Okay, so here we've got copper dipped into copper nitrate, and we've got zinc metal dipped into zinc nitrate. Here's a voltmeter to measure the potential difference, and this is the salt bridge. It's just cotton wool dipped in potassium nitrate, and then the potassium ions can go drop, 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 and the nitrate ions can go drop, 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 and we can keep this whole thing nice and neutral. This thing here is called the standard half cell, and it's what we measure everything else against. If you look at the redox table, it's right in the middle of the redox table, and it has a potential difference of 0. So all we do is we measure all the others against this as a standard. That's all. So we need to know off by heart, what does it look like? The hydrogen gas or hydronium half cell is the standard against which we measure all the others, and we give it a 0. And it's H pluses gain 2 electrons to become hydrogen, and hydrogen loses 2 electrons to become H plus. To measure other half cells, the standard electrode potential, all concentrations must be 1 mole per cubic decimeter, all pressures 1 atmosphere, and temperatures 25 degrees centigrade. So those are our standard conditions that we use to measure half cells. This E0 value or E theta value refers to reduction potentials. The oxidation potential exactly equal but opposite in sign, and we'll talk about that in a little bit more detail in a sec, really tomorrow. Best reducing agents are at the top of the table, best oxidizing agents are at the bottom of the table. So the thing at the top of the table is likely to be oxidized, and things at the bottom of the table are likely to be reduced. Half cells high on the table are most likely to form the anode, and here we go, A, C. The letter A higher is anode, lower is cathode. A comes before C in the alphabet. Not very tricky to remember. And then this is just a picture of this standard half cell over here. In comes the hydrogen at 100 kilopascals, which is atmospheric pressure. There's a platinum wire to allow the reaction to take place. The salt bridge is obviously going to something else over here. This is just a half cell, remember. You need 2 halves to make a whole. And then there's some hydrochloric acid over there. And of course, hydrochloric acid makes H plus ions for us.